Okay, is that running? Yep. Okay, so section 2.1. So first, let's just note, a system of equations. This is not new, a system of equations. A system of equations, we've just been solving them. That's what we were writing out, is it was a system of equations. So a system of equations is more than one equation and more than one unknown. So you could have, say, two equations and two unknowns, like x plus y equals 3 and 2x minus y equals 0, something like that, right? And that's sort of what we were solving. We had a and b, but that would be two equations and two unknowns. The x and y are what we don't know, right? And to solve a system is to find an answer that works. Okay. So, does anyone know the solution of this one? Without solving it? Okay, x is 1 and y is 2. Yeah, that would work. So there, you found the solution. How many solutions are there? No, you're getting, and that's why I'm asking, because if we talked about this first in the course, you would have told me just one, because what are these equations? What if we draw them? Don't think of linear algebra, think of their lines, and if two lines have a solution, they intersect, and that would be the solution, is the point where they cross. Right? So there's only one solution. There could be infinitely many solutions, but what would the lines have to be to have infinitely many solutions? No. So straight lines we're talking about. What's that?
Wouldn't they have to be two sine waves or something like that?
No. Yep, so straight lines. How could two straight lines have infinitely many solutions?
If they're the same line.
If they're the same line, right. So they're just, I always call it a disguise. Yeah. You take one line, multiply it by 2, it's still the same line, all those points still work. So two lines being the same. And that was actually the mistake I made in 1.5 just a minute ago when I left that one out, that one where the two equations were the same. I just dropped both of them instead of considering one of them, right? That's where the mistake was. So this is situation 1. Situation 2, so this is, we would say this has one unique solution. And in math, when we say one unique solution, it just means one solution. Okay, so don't get confused with the word. So if we had, for example, this one, I'm trying to make it look very disguised. So the hint is telling you that I've disguised the second equation. So are these the same two equations? Yeah. If I multiply this one by 3, what do I get? 2x minus 3y equals 6. They're the same equation. So multiplying an equation by a non-zero number doesn't change the equation, it just makes it look different. Okay? It's like you changing your clothes. You look different, but you're still the same. Okay? So remember that, because that becomes important later. So this, since they're the same equation, there are infinitely many solutions. Now, we're going to start writing them out, sort of what I did in the last one. So if these are the same line, you only need one of them. Okay, so but we still have to keep one of them. So keep one line. So let's say 2x minus 3y equals 6. Solve for one unknown. Say x, solve for x. So 2x equals 3y plus 6. Divide everything by 2. Okay, so that's just the equation rearranged. You could solve it for y. You could even have taken this one and solved for y. It doesn't matter. Now our solution is x equals something and y equals something. So here we've solved for x. So we're going to write that down for the value of x. 3 over 2y plus 3. And this is saying that we need y's in all of our equations. So what would y be? Just y. This is saying choose a value for y, plug it into both, and that will be one solution. Choose another value for y, plug it in, and that will be a second solution. And you could keep doing that forever, and that's the infinitely many solutions. Now what we usually do here, a little later, we'll say let y equal t, and this will look less confusing. So you'll have 3 over 2t plus 3, and y is t, where t is any number. This is the infinitely many solutions. And that's because they were the same line. So if you plug 0 in, what would we get? X would be 3, if you plug 0 in, and y would be 0. That's one solution that will work. So if we let t equal 0, then we'll have the solution 3, 0. If we let t equal 2, what would we get? I chose 2 on purpose so that that fraction would cancel. So 3 plus 3 is 6, and y would just be 2. All right, and you could keep going, and those would be a list of all the possible solutions that would work in that equation. What's this called, writing it in this way? Parametric form. So that's a parametric form of an equation of a system, or solution to a system of equations. It's a parametric form. And we saw a parametric form. Now, in high school, you solve these, and they just avoid the ones that are infinitely many solutions. It either has a solution or it doesn't, and they don't talk about this because then that's confusing. Right? But it matters after it's just in two variables, because you could have parametric, or you could have infinitely many solutions when it's not the same line, because you could have a plane with a line laying in it, and all the solutions on the line would work in both. Right? So you can have infinitely many solutions without it being, the two equations being the same. Okay? So that we will see after. And what's the third scenario with the system of equations? And what does that mean? What would the lines look like? Right, parallel lines don't. And how would you recognize, without doing the work, that something had no solution? Yeah, so if I wrote these, let's just say, so these have no solution. I started off like if 2x plus 3y, if we multiply those by 2, we get 4x and 6y. Do you see that? But is this side multiplying by 2? No. When they're disguised, the whole equation, even the right-hand side, is a multiple of the other. This has the same slope, the direction vector is the same, but the point that they're attached to is different. Right, so if we wrote this in vector form, for example, or if you went back to high school, you'd say the slope is the same, but they have a different y-intercept. Right, same idea. If you went to solve these, say we multiplied this one by -2, we get -4x minus 6y equals -2. Rewrite the second one. These cancel, so we get 0 equals 2. No solution. Now in R2 it means they're parallel, but in R3, think about 3 lines. Just 2 of them would have to be parallel and the third one doesn't have to be. It could cross, but there wouldn't be a solution to all 3. So let's talk about that. We'll learn how to actually solve it later, but let's write one out. So in R2, every equation that we write is a line, but in R3, every equation we write is a plane. So these are planes instead, right? So it's a little harder to see, but let's say that this had one solution. Let's say that that was the scenario. So we would say one unique solution. It's maybe hard to visualize, but what might this look like? Oh, I still have your highlighter. Whose highlighter did I borrow? Yes, don't forget that. Look, I just see it right now. Can you see these 2 planes? Did I do an okay job? It's very hard to draw them. So I don't know if you were able to or not, but I'm just going to color one in blue there. Can you see them? So these are 2 planes. So this would be 2 equations, 3 unknowns. A plane has 3 unknowns, x, y, z, but this is only 2 equations. How can I add a 3rd equation so that it only has 1 point in common? Where would the plane have to go? Yeah, like think of it straight up and down through the middle of those, almost like a star, and I don't think I can draw this so that it will look right. So, whatever you... My hesitation, I don't even know how to start doing this. Someone else is probably better at drawing these than me, but... So, this will... Anyway. So, if we add a 3rd one in, going another direction, then they could cross at 3 points. Okay? And that is if these ones cross at a line, and then this one cuts through that line. Right? That would be one unique solution. That's how that would work. So, how do you think we could get, the next type of solution is that they can have a line as the solution. So this is a point as the solution. So how could they have a line as the solution? Okay, so there's back to my 2. Yeah, this line they have in common. Right, we could have another one going through that same line. So I think I can actually draw this better, because I can add another one. There. right? Do you see it? So they go through a line. And so instead of the plane being flipped the other way and just having that point in common that's on the line, but it's just a point, we have the whole line as in a part of the solution. So here we can have a point as a solution, a line as a solution. So this would just look like x, y, z. This one is a line as the solution. Let's do it like that. A line as the solution would look like a point plus a direction times t. Because we're going to be doing it all in vectors as the answers, right? So a line in 3 space is in vector or parametric form. We actually are going to start with parametric form and convert it back to vector form. But that would be a line. And then what other type of solution could we have? Yeah, how could a plane be the solution? Yeah, and then if we all 3 would have to be the same. So that, it could happen. If the plane is the solution, that means all 3 planes were the same plane, right? So let's write it down. So that would be all 3 planes are the same. So I probably wouldn't give you that ever, but it is a possibility, right? If we disguise 2 planes. And then 4, no solution. So what might happen here, no solution? Yeah, exactly. So the other plane doesn't cross through that line. So how could we draw the third plane that it doesn't cross through that line? Because as soon as it crosses through that line, we have a unique solution. Yeah, it could be parallel and going through a different line. So it could be like over here. Yeah, now it's looking like these are crossing here, but that would be fine because all 3 don't cross in the same place. The picture I drew in my notes was more like I put it up here, flat across the top, right? So it crosses this one here and this one here, but it doesn't cross that line, right? So kind of think of it like a triangle, right? One plane's going this way, one plane's going that way, and then the third is here, but they cross all of them at lines, but not any of the same ones, right? So all right, so a system of equations, we're just going to rewrite that one, or any, it doesn't matter what the letters are. So a system can be written as a linear combination. So a system of equations is actually another form for a linear combination. So here we have x, y, and z as our unknowns are actually our coefficients for our linear combination. And what would go here? What is x multiplied by in this first row? 2, 5, 1. And y is multiplied by 3, negative 3, negative 1. Z, negative 1, 2, 1. And on the right-hand side, 2, 4, 6. Right? So that's actually the same thing. It's just a different form. So. It's asking if these planes intersect, right? Remember, the 2, 4, 6 is just part of the plane. It's like the point that it's attached to. So that's the, yeah. Well, it's the point that this plane is attached to. Like, the 2 is for the first one. It's nothing to do with it as a whole. Yeah, yeah. But yeah, if you're writing a plane in vector form, then you're right, that would be the point it's attached to, but this is a little bit different than that, because this is 3 planes and we're trying to figure out whether we have a point in common. Okay, so that's just writing it over, and we already did this, didn't we? Because we wrote the linear combination with ABC here, and then we wrote it in this form and then tried to solve it. So we already did that, this is just going backwards. We can write a system and we'll call it multiplication form. And usually you'll see a question, for instance, say, write the system in AX equals B form. So we often just call it AX equals B form, not multiplication form. Okay, so this is, so same system. Multiplication form looks like this. 2, 3, minus 1. So I get 2, 3, minus 1. 5, minus 3, 2. 5, minus 3, 2. And then what would the last line be? 1, minus 1, 1. X equals B. So this is called matrix A, this is called vector X, and this is called vector B.
Why is it a big A and then a little?
Because matrices are always, it's a good question, because we'll get to that soon, but matrices are always denoted by a capital letter. Vectors are a small letter, and in the book, they're supposed to be bolded. I know sometimes they, instead of putting the arrow on top, they'll bold. Yeah. Or maybe not in italics, that would be another way to see it. But it's a small letter for matrix, or for vectors, and a capital letter for, with no special symbol. No arrow on top or anything like that. And then augmented matrix form. So this is what the form looks like. Square brackets always, when we're doing matrices. And this is like an absolute value line. It's just a line. It doesn't have, like, it's not curved. Some books will put it as a dotted line instead of a solid line, but it is just a line, and it's like the equal sign. So here we just take A, and that line, you would say, augment it with B. So this is A augmented with, with B. That's how you would read that. So we take A, 2, 3, minus 1, 5, minus 3, 2, 1, minus 1, 1, whoops, and augment it with B. So straight line here, and it usually, if you're going to do it correctly, it extends a little higher than your square brackets on the sides. Okay, so it's like a separator line, it's just the equal sign. So that's writing the matrix, or the system, without actually writing the X. Okay, so it's another way to hold the system, and this will actually eliminate all these confusing X, Y, Zs when we go to solve it. So let's take a break, and then we'll do a little more of this section after the break.